Hello student, welcome to the wave optics course. Today we have lecture number 33 and in today's lecture we are going to discuss about the single slit diffraction problem. So already we have started this problem in earlier class. So we have lecture number 33 and in the last class we mentioned that we try to calculate the Fraunhofer diffraction pattern of an aperture like this. So, we have an aperture here which is essentially a single slit. And then the light is falling here, the plane wave that is coming here, and then we have an aperture, it then hits this aperture and we introduce a linear oscillator model here that when it hits the aperture, then this portion of this aperture allow the light to pass through, but here at this portion we have the location of linear oscillators, and then waves are emitted from these oscillators. And if I place a lens here, then at some point P this hits here, and then it converges to a point P, and we want to find out the intensity distribution at P, that is the overall structure. So, this is the light waves that is passing through this aperture, and then they are allowed to merge at some point P on the screen, and this is the lens L. So, what we find that if I magnify this portion, these are the individual oscillators which emits the waves. These are the light waves that is moving like this. And then it converges to a point P. So, what we were doing is we add all the contribution of this wave, and in order to do that we name the waves as E1, E2, E3 and En. If I consider n number of oscillators, then these are the field of the waves that is coming out, where E in general E j was E 0 amplitude e to the power of I k r j minus omega t. That was the form of the wave, and the total field E t, for example, it is sum over all the field E j. J goes to 1 to n, and we did this sum, and when we did this sum we get some value, and let me write down that value. So, my total electric field E t was E naught e to the power of I k r j sorry k r I k r 1 rather omega t, that was the term that we take common, and then we have something like e to the power of I n k delta by 2 whole divided by e to the power of I k delta by 2, that was the term, and then multiplied by one important term, and that was sine of n k delta divided by 2 whole divided by sine of k delta divided by 2, where delta is the important term and that is so delta here, delta was a of sine theta, where a is this distance between two consecutive source point, and theta is this angle. This is the angle theta. So, k delta divided by 2, that term was essentially pi a sin theta whole divided by lambda. That was the value. Also, this k delta, this quantity we write as phi, and then we try to write this entire equation in terms of the intensity. The intensity, which is proportional to the total field mod square, and can be written as intensity, which is essentially a function of phi or theta, whatever it is, some intensity I naught, then sine square n phi whole divided by sine square phi, where phi is equal to k by 2 delta, which is pi a sin theta divided by lambda. Okay, that we derived the last class. Also, one thing, d, if the separation of the aperture, the width of the aperture rather, is d, then d is equivalent to n plus 1 a. If a is the number of if a is the n is the number of linear oscillator and a is the separation between two consecutive linear oscillator, then that is the relationship between d and a, and that is constant. That is, n the number will going to increase if a is decreased, but their multiplication will remain conserved. So, when n tends to infinity, then A tends to 0, that is the condition. So, for very large n, so for large n, D is nearly equal to n A, and essentially my I is I naught sine square n phi whole divided by sine square phi, that is the original expression, and then n phi is n A pi divided by lambda sin theta, that is equal to d pi divided by lambda sin theta, and phi is that quantity. So, for small phi, sin phi is nearly equal to phi, that is another thing. So, essentially I, which is a function of phi, can we write down as I naught tilde sin square n phi by phi square. That is the thing we derived in the last class. So, I redo that, where phi is that quantity pi A whole divided by lambda and sin theta, that is the value of the phi. So, now I modify, today I like to modify this thing slightly. So, I theta, which is a function of phi or theta, that I can write I naught tilde, then I write n square, I will write an extra n square here, sin square n phi, and then in the denominator I have n square phi square or n phi whole square. So, I add one n square here in the numerator and then add another n square, so that this n square will cancel out and I go back the original expression. By writing so, this expression is now have a specific form, and it is I 0 then sin square beta whole divided by beta square, where my beta, which is n phi, which is pi d sin theta whole divided by lambda. So, that I write here, and that is the expression we have, that is the intensity distribution expression. And now, if somebody wants to plot it, this is called a sinc function, then the intensity will look like. So, overall picture will be like this. So, I have an aperture here and we have a sinc function. So, it will going to distribute like this way, the intensity will going to distribute in this way. This is square of the sinc sinc function. So, the intensity of this distribution will be like this. So, if I draw here this function, that will be a central maxima, and we have a symmetric kind of distribution of the intensity like this. So, that is the intensity pattern one can expect. So, this value is the peak value is I naught, and this is the direction, this is the change of beta, and beta is this quantity. So, change of beta means essentially for a fixed wavelength it is a change of theta as well. So, here you can see that the intensity is I 0, and when d is very greater than lambda. So, d is very greater than lambda means when beta is a relatively high value, then with the slight change of theta there is a very large drop of this amplitude peak. So, we will going to discuss more about this structure now. So, so we have a minima on these points that one can readily figure out with this expression, that it is when the beta value is in pi, then all the cases this will be 0, and we also have some maxima, and we are going to calculate what is the condition to get this maxima. But before that, once we know this is the structure of the intensity distribution that one can get from the single slit diffraction pattern, as this get as a single slit diffraction pattern. So, this calculation now we will do in a more general way without assuming the linear oscillator model, and that is a straightforward single slit diffraction calculation, and also we proceed this calculation for double slit and multi slit. So, let me first develop this calculation. So, this is single slit diffraction problem, and this single slit diffraction problem we, instead of doing a discrete summation, now we will do a constant summation in this way. Let me draw that. So, this is the single slit we have. So, this is the slit width, and let me draw the coordinate. This is the middle point of the slit, and suppose this is my x axis. So, this is my x axis, and along this direction I should have y axis. Okay. So, this is the point, I called this point the central point as 0 0 point, and if I move, if I take a small section here, this small section dy, this dy is at the point of y, okay, and this is my central point. So, coordinate wise, if this entire width is d, then this point is dy 2 and this point is minus dy 2. This is the coordinate of these 2 points, y coordinate, and x coordinate is 0, because this line I consider x equal to 0 over x equal to 0. Now, the ray will come from two rays will come from these small sections and another will be from 0. So, the electric field that is coming out from this small section at some point P is dE. So, dE is the electric field that the contribution of the small section that is coming at some point P. So, that value dE will be essentially amplitude E naught and then e to the power of I delta and dy. So, field at any point P due to dy is this. So, this is field at any point P due to the aperture dy, that is the amount of the field one can have. And delta, what is delta here? That is important. Delta is the phase difference between the point y 0 and y. So, this so simply I write the phase difference, the phase difference between the point y and y plus dy. So, the phase difference between these two are essentially, so that means if one ray is coming from this line and another ray is coming from this line or another wave. So, the phase difference one can calculate by joining this. If this angle is theta, this will be theta. So, the path difference one can calculate the path difference delta is y sin theta, because this is the extra path difference. So, this is the extra path difference we have, this value is y sin theta, and the phase difference comes out to be 2 pi by lambda y sin theta, or it is simply k naught multiplied by path difference delta. So, that is the phase difference. So, I calculate phase difference and that is this. So, this I can write also as big K multiplied by y, where big K is 2 pi by lambda multiplied by sin theta, and for a fixed angle this is constant. Okay. So, now the total, this is the contribution of D. So, the total field, that is the goal of our problem, the total field at some point P, the total field at P will be the superposition of all the contribution, and the superposition of all the contribution means I need to integrate over this field over the range of D. So, E t, the total field will be E t, and that is integration running from minus d by 2 to d by 2 and dE. So, essentially I am using the same principle that we have done earlier, that summing over all the contribution of the linear oscillator, individual linear the field that is emitting from the linear oscillator, we combine everything as a sum. Here we are doing, but in a continuous manner. In previous approach we calculate as a discrete sum, but now we are doing this as a continuous sum by integrating these things. So, dE, I know what is dE. So, this is E naught, then integration minus d by 2 to d by 2, that is the limit, and then e to the power of I delta, and then we have dy. Note that inside the delta I have y, delta is ky. So, let me do this integration here. So, Et total field at some point p is E naught integration minus d by 2 to d by 2, and then I have e to the power of I b k y dy, where b k is 2 pi by lambda into sin theta, and that is constant here. This integration is very straightforward. So, we have E naught e to the power of I of k y whole divided by I k, sorry, I b k, and it will be d by 2 and minus d by 2. And that is simply E naught and when you put this d by 2 plus d by 2 and minus d by 2, we simply have 2 I sine of k d by 2 k d by 2 whole divided by the denominator we have k d by 2, and also one I will be there, I, and this d by 2 I put because we in here we have a d by 2. So, what I do, I will multiply a d by 2 altogether to make it as a sinc function. Okay. So, this is essentially E naught d and then sine of k d divided by 2 b k d divided by 2, and here we have b k d divided by 2. So, this is E naught d sine of pi d divided by lambda, because I am now putting the value of the k, it is pi d divided by lambda, and then we have sin theta whole divided by pi d lambda sin theta. Now, this we write as I mean this quantity I can write at E naught d sine of beta divided by beta. So, you may note that this beta we already defined, I mean in this calculation. Let me go back. So, beta was pi d sin theta divided by lambda that we calculated, and the same notation I will use here, that pi d divided by lambda sin theta is my beta. So, after having that, I can write that my intensity should be proportional to the total electric field square of that. So, intensity can be written simply as I naught sine square beta divided by beta square, the same expression that we derived in the linear oscillator model, but here we did the continuous integral. So, where beta is pi d sin theta divided by lambda, and the intensity will be distributed in this way. This is the distribution of the intensity. This is the peak intensity along this direction. We have I as a function of theta or beta, and this side we have beta, which is this quantity. Now, if I want to find out that what is the maxima and what is the minima, then it will be easy. So, quickly let us find out. So, this is the point we have minima. Let us find out the minima first. This is the point we have minima. So, for minima, beta will be simply n pi, where n is an integer, but note that n should not be equal to 0. So, n is 1, 2, etc. So, sin when beta is n pi, so sin theta n will be n of lambda divided by d, because beta is pi d sin theta by lambda. So, instead of beta, if I write n pi, so n pi is pi d sin theta divided by lambda. So, theta n should be n lambda divided by d, n lambda divided by d. So, these are the thetas at which we have minima. So, how these things will look? So, the structure will be like this. So, we have a structure like this, and it goes to infinity with reducing amplitude. And if I calculate from, this is the slit width, and if I calculate, this is the theta, this is my 1 theta for which I have a minima, then we have another theta here for which we have another minima, and all these things. So, this theta is lambda divided by d, this theta is 2 of lambda divided by d, this theta is 3 lambda divided by 3, and so on, 3 lambda divided by d, and so on. So, this is the point we have where we have minima. Now, quickly understand where we get in which point we get the maxima, but I think I do not have much time to discuss about this maxima. Today time is up. So, in the next class, what we try to describe for this single slit pattern, that how one can calculate that at which theta we will get the maximum points. So, that is a bit tricky thing, but we will try to figure out by using something called transcendental equation, that how one can find out the location of the maximum peaks when a light is diffracted by a single slit under Fraunhofer diffraction pattern. So, with that note, I would like to conclude here. Thank you for your attention and see you in the next class.